In this video, we're going to calculate our second derivative together and then use it to find some slopes of the tangent lines at a few different points. So here we're going to find f prime of x, which is the notation, one notation for the derivative of f of x equals 3x minus x squared. All right, so we have to do that before we can actually find the slopes of the tangent lines. So let's get started. From the previous video, we remember, I hope, or maybe look back at your notes, what the formula for the derivative is. Okay, we've got f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. If you'd like to use h in place of delta x, you are more than welcome to do that. It doesn't make a difference if you want to replace h with delta x everywhere. Again, I like the delta x because it reminds us what we are doing. We're finding the slopes of secant lines and then making those 2 points get closer together so that our secant line becomes a tangent line. Now, in all of these cases, we always will have a difference quotient that we need to simplify first. And then we will have a limit that we need to calculate after. So the first part of the difference quotient, the hardest thing here might be to figure out what this first part is, the f of x plus delta x, or the f of x plus h. So what that's going to be in this case maybe pause this video to see if you can figure out what this is on your own. We're going to plug in an x plus delta x into every place that there's an x in the original function. That's in two different places. So we're going to put an x plus delta x for x here, and then also an x plus delta x for x here. So this will end up looking like not 3x, but 3 times x plus delta x in parentheses, and not minus x squared, but minus x plus delta x squared. Now we're going to have to simplify this by expanding it out in our difference quotient. If you want to do this all in one step, you can. If you want to do it in separate pieces, it's a little bit easier to keep track of. So again, I know we're going to want to just expand this part out eventually in the difference quotient. So let's go ahead and just distribute and maybe combine any like terms that we might have. Okay, so we're going to distribute the 3 into the parentheses. We'll get 3x plus 3 delta x. Then we have to FOIL out or double distribute this x plus delta x squared. Okay, we did that in the previous video, but if you need to do some extra work on the side, please go ahead. This will be x squared plus 2x delta x plus parentheses delta x squared. Lastly, we should distribute this minus sign into those parentheses. So we're just kind of liberating everything, making sure that there are no more parentheses anywhere where we can eliminate them. So we'll get 3x plus 3 delta x minus x squared minus 2x delta x minus delta x squared. Okay, then we have f of x in our difference quotient, looking up here at f of x. That is, of course, just the function. So this will just be 3x minus x squared. And then delta x will always just stay as delta x. So let's go ahead and plug this in. So now this whole thing here, well, we're going to do the limit last. So let's keep limit as delta x approaches 0. Let's put in that whole expression for our f of x plus delta x. So it'll be 3x minus 3 delta x minus x squared minus 2x times delta x. Oops, don't need those parentheses. Minus delta x squared. Okay, so here is the pink, the f of x plus delta x. Then we have minus all of f of x. So that's 3x minus x squared. Now we're going to be subtracting all of this, and it has 2 pieces to it separated by a minus sign. So it's very important to make sure that we have parentheses around the f of x in the definition here that we're using. Okay, and this is all divided by delta x. Okay, the procedure with these, if you recall from the last video, and just in general with our difference quotient simplifying from section 1.4, our functions review, we want to be able to cancel out this delta x in the denominator. That's going to mean simplifying everything in the numerator as far as possible, and then trying to factor out a delta x from the numerator. And then we can try to cancel it with the denominator. So the next step here would be to distribute this minus sign and get rid of those parentheses so that we can then cancel some terms out. It is really fun because we always have a lot of things that just kind of end up disappearing and canceling themselves out. So I'm just going to rewrite this entire first pink chunk here. Then we're going to distribute the minus sign. That'll give us minus 3x, and then plus, sorry, not 3x squared, but just x squared. Okay, now let's see what we have that can cancel out. We have 3x minus 3x. We have minus x squared plus x squared. And then I think that's it. There's no more like terms for us to combine together or cancel out. So what we have up top in the numerator that's left over will be negative 3 delta x minus 2x times delta x plus delta x squared. And looking back on this, I'm not sure why I made this a negative. Sorry about that. This positive here, if you caught this before and you're really confused, I apologize. This plus here, I don't know why I made that a negative. I just copied it wrong. I'm sure you can relate to doing that sometimes. So actually that should all be a plus down the line. So positive 3 delta x minus 2x delta x plus parentheses delta x squared. Sorry about that. Okay, but then we still do have over delta x. I think now is a good time for us to factor out the delta x from the numerator. Okay, what we'll have is 3 minus 2x plus delta x to the first. And then here is the time where we can remove the 0 over 0, the places that isn't allowing us to calculate this limit. And what we have left over is 3 minus 2x plus delta x. I think now is a good time where we can use some direct substitution. Remember what we are doing with direct substitution is we're letting delta x, that whole symbol that's two things together, or h, approach 0. So we just plug in a 0 for delta x. And so we find that our derivative for our function that we started with is 3 minus 2x. All right, so here is f prime of x for the function that we started with. Remember that this is the slope of the tangent line to the original function, to 3x minus x squared, at any x value that we might choose. So looking back at what the question is asking us, right, we want to find the slopes of the tangent lines at various places. Okay, so let's see, let's start with, so we've got 1, 2. So let's start with that, the point 1, 2. 1, 2. So that point is right here, 1, 2. If we sketch the, just by eyeballing what the tangent line will look like, that's going to look like this. Something like that. Again, we don't want to estimate this graphically. We want to use the derivative. This formula that we have here, 3 minus 2x, this is going to give us the exact value of the slope of this line that we just sketched. So the slope of this line is going to be whatever we get when we plug in an x value of 1, because in our coordinate here, right, we've got 1 as the x value. So let's see, f prime of 1 will be 3 minus 2 times 1. So we're just plugging a 1 in to the derivative because that's our x value at this point. 3 minus 2, that's 1. Okay, so that's the slope of this line. Slope of that line there is equal to 1. Okay, the next one we want to do is 2 comma 2. So that is over here. Maybe I'll use a different color this time. Let's try a darker green. So right here we've got 2 comma 2. And we have this symmetry here. So, maybe the slope of this line should be -1, just because of what we found before. These lines are sort of perpendicular. But let's see. So this dark green one, we'd plug in now 2 into our derivative because that's the x value of this coordinate that we have, 2 comma 2. Okay, so it'll be 3 minus 2 times 2. Okay, so that's 3 minus 4. And so that is actually -1. So that's the slope of that tangent line there. This is so easy, right? Now that we have this formula for it, it's so fun and easy. We just did a little bit of work in the beginning, and then we get all this neat stuff for free. The last point here we have is 3 comma 0. So let's see, we'll use purple for that one. So we've got 3 comma 0. So that's this point right here. If I just sketch in and eyeball a tangent line, I don't know, it might look something like this. It's not the best sketch. It's a little wobbly, but that's okay. So the x coordinate here is 3. So we'll plug in a 3 into the derivative. That'll be 3 minus 2 times 3. That's 3 minus 6, and so that's -3. And so that's the slope of the purple tangent line. Pretty cool. Okay, so this can extend to any sort of function that you have, any point that you want to find the tangent line at, anything at all. This is the really powerful thing about the derivative, is that it tells you the slope of the tangent line anywhere. Let us look at one more example with a radical function. So we're going to look at f of x equals the square root of x. Our second example is a radical function. So we're going to look at the function f of x equals the square root of x. And this time, we don't only want the slope of the tangent line, we want to find an equation of the tangent line. So our answer in this case is going to not be a number, but it'll be something of the form like y equals mx plus b, right? That's an equation of a line. So we want to look at the point 4 comma 2. So here's a graph of the function y equals the square root of x. And the point 4 comma 2 is right here. When you plug a 4 into the function square root of x, you get 2 out. And well, if you sketch in the tangent line, I don't know, that might look something like this. Something along those lines, maybe a little straighter. It's hard to make things perfectly straight. So here it is. We want to find an equation of this thing. Just to back up a little bit of a review from domain, this function starts here and it goes on forever this way, right? It doesn't have any part of the graph that has any negative x values, and that's because you can't plug in a negative number into the square root of x. So only 0 or more. Okay, so in order to find this equation of the tangent line, again, we want y equals mx plus b. And m, the slope, is going to be given to us by the derivative. More specifically, f prime the derivative evaluated at 4, right? Because that's the slope of the tangent line at that point, 4 comma 2. So the first thing that we want to do is find the derivative, because that's going to give us the the formula for the slope. All right, so f prime of x is the limit as delta x approaches 0 of f of x plus delta x minus f of x all divided by delta x. Now f of x plus delta x, okay, what do we get when we just plug in x plus delta x into the function? Well, that'll just be the square root of x plus delta x, all underneath the radical. Okay, again, so f of x plus delta x is just the square root of the entirety of x plus delta x. Then f of x, that's just the square root of x. Okay, again, f of x here, that's just the square root of x. And then in the bottom, that's just always going to stay delta x, right? So in the bottom here, we just have delta x that will stay as delta x. Are we catching up? Okay, here we go. So I hope these colors help, right? Just to help you see like where everything's going. Like, so we have this general formula that we start with for any old function. Then the second, or I guess the second thing we do after we write that down is to see what happens for our particular function, right? We had the radical function, and so here's what that looks like. Now we can't just cancel these delta x's. Can't just cancel the one in the bottom with the one that's underneath the radical. The one underneath the radical is really held inside by the radical there. The way to access things inside of roots like this is by using that algebraic technique that we reviewed a while ago called multiplying by the conjugate. So that's what we're going to do here. Okay, so to multiply by the conjugate, it's really multiplying by the conjugate over the conjugate. Okay, so we look at the things that have the radicals, and we change the sign between them. So this will be radical x plus delta x, and then not minus but plus radical x. Same thing top and bottom. Just like that. And it's always a really great idea to stick parentheses around things that have more than one term in them when you're multiplying. A lot of times we have to like kind of FOIL stuff out or do a little more work than what it might look like at first. Okay. Now, when we multiply these together, we're going to get a single fraction. Right? When you multiply fractions together, you multiply their numerators and you multiply their denominators. Excuse me. In the denominator, you are going to get delta x times the conjugate. Remember that our goal is to cancel out the delta x. So that means you want to leave it factored in the bottom and not distribute it. If you distribute it, you're not going to be able to see that it can cancel out. So in other words, just don't do extra work. You're making it way harder for yourself if you try to expand this in the denominator. Just simply write it as that product. Factoring is simple. It's the simplest form, and this is already factored, right? So just to make that really clear, you want to always leave the denominator factored, or in other words, don't distribute the delta x inside ever. Don't ever, ever, ever do it. It will never, ever, ever help you. However, in the numerator, you do want to distribute because we want to be able to, like access things under the roots. Now remember, when you multiply a thing by its conjugate, this is actually a factorization of a difference of two squares. Okay, so the idea with the numerator, when you multiply something by its conjugate, you square the first thing, the middle term cancels out, and then you subtract the square of the second thing. So in other words, we're going to square the first thing. Okay, so we'll get radical x plus delta x squared. That's playing the role of the a in the little formula I have over there. And then the b is radical x, so we'll square that too. And then it's always a minus in the middle. If you want to FOIL out the numerator and see that, you definitely can do that as well. But the idea is that that middle term, which would have a radical in it, would cancel out or not be there. And so that's why this conjugate stuff is useful, because it gets rid of the radicals. So when we square a root, they just go away, right? So we just cancel those. So we'll get x plus delta x and then minus x up top. And again, don't do anything in the denominator. I know math can be hard because you don't know when to do what and stuff, but it just takes a little bit of practice. And so yeah, we're practicing. In the numerator, we've got x minus x, so those add up to 0. What that leaves us in the numerator is a delta x. In the denominator, we still have delta x, and then that's times all of this stuff, the conjugate in parentheses. Here is where the delta x's will now cancel out. They're going to divide to give us 1. And just think, if you had this distributed inside to here and here, and would you have been able to see that? I don't think so. You'd have to then factor out the denominator in order to cancel it. And you're just causing yourself like to lose, precious time and all that stuff. So don't bother doing that. So what we have here is a 1 up top. We've got a radical x plus delta x in the bottom, and then plus a radical x. I think now we can actually direct substitute, right? We canceled out the 0 over 0. So now we can actually plug in a 0 for delta x. That puts a 1 up top. We'll have a delta x plus 0, a radical x in the bottom. We just put a 0 in for delta x, and then plus another radical x in the bottom. Now in the denominator, we have radical x plus itself. These are like terms that you can combine together. So we've got a thing plus the same thing, and so this would just be 2 of those things. 1 over 2 radical x. And there is our derivative. Okay, so for f of x equaling radical x, the derivative that goes with that one is 1 over 2 radical x, right? That's what we just found. Now this isn't our answer, right? We're looking to use this. We're looking to use this to find the equation of that purple tangent line there. So what we have to do, now we can find m. So we're looking for y equals mx plus b. Right, the slope m is really like m tan, tangent line slope. This is going to be given to us by the derivative evaluated at 4. So f prime of 4. So we're going to plug a 4 in to the derivative, right? Because 4 is the x value that our point is at, right? 4 comma 2. So we'll plug a 4 in, we get 1 over 2 radical 4. That's 1 over 2 times 2. And so that's 1/4. So there's the slope of that line. Okay, now we have to find b. Okay, so the way that I do it is I just put in the slope. And then we plug in the point. Normally we'd have a choice, but here we only have one point that the tangent line is going to go through that we know of. So 4 comma 2, just make sure that you plug in the 4 and the 2 in the right spot. So 2 is y and 4 is x. Okay, 2 equals 1/4 times 4. 1/4 times 4 is 1. And so that tells us that, what do we have here? Subtract 1 from both sides. So 1 is equal to b. And so putting all of these together, these two things together, the value of b and the value of m, we can write our equation of the tangent line. So it'll be y equals 1/4 x plus 1. And there we go. That's what we're looking for. That's the answer to our question. So my sketch is a little off, right? The y-intercept isn't quite right. Maybe I could change that. That's close, but you know, this is, I don't know, maybe that looks a little bit better. And yeah, so here's the equation for that. Now, when you're checking these things on your own, or when you're trying to, you know, like figure these things out on your own, you should probably graph the function and its tangent line and make sure that you don't, you know, if we got something like this, that wouldn't, you know, we did something wrong. So if you have a graphing calculator, that's a really nice way to do this. Just plot both of the function and its tangent line on your graphing calculator. Or there are websites you can use. Desmos is one of them. And there's others like GeoGebra. I have a list on Blackboard if you want to go look at that under math resources. So stay tuned in the next video. We're going to talk about something called differentiability, an extension of this example and this function here. See you soon.